guys, welcome back to the channel. It's been months since I posted something about research paper or something projects about. Today we are going to something deep dive into the reasoning of LLMs, how they respond and all things, how they think. So have you ever noticed something strange about AI? Sometimes it solves a complex maths problem perfectly, and the other times it feels that something a 10-year-old could solve. Why does that happen? What if the problem isn't how smart AI is, but how it thinks? Today, we are going to explore one of the most important discoveries in modern AI. That's chain of thought prompting, a simple idea that suddenly unlocked reasoning in large language models. This research was done by scientists at Google Research Brain Team, including Jensen Van Zwing, and it was published in 2022. It changed how we understand intelligence in AI. Let's look at the core idea of the paper. The author discovered that if you ask an AI to show its reasoning step by step, its ability to solve complex problems improves dramatically. Like, what does this mean? Normally, when we ask an AI a question, it jumps straight to the answer. But humans don't do that. We break the problem step by step. That sequence of steps is called chain of thought. Here's the shocking part. These reasoning abilities don't appear gradually. They emerge suddenly, only when the model becomes large enough. Think of it as like a small AI model. A small AI model is equals to a student memorizing formulas. A large AI model, that is equals to a student who actually understands math. So reasoning suddenly appears at scale, and the results were huge. Using just 8 examples, like a model called PALM 540B achieved a state-of-the reasoning performance on math world problems, even beating specifically trained models. Now let's look at the most important figure in this paper. This is simple. Like, here the model is asked, Roger has 5 tennis balls. He buys 2 cans, each has 3 balls. The model directly answered, the answer is 11. Looks correct. But look at the second question. It says the answer is 27. That's wrong, because that model didn't show its reasoning. Now look at the same questions, but this time the model explained step by step. This looks exactly like how we solve the problem. Step 1, step 2, step 3 and final answer. And because the model follows a reasoning process, it gets the correct answer. So the main idea of the paper is AI doesn't fail because this isn't smart. It fails because it isn't thinking in steps. And when we force it to think step by step, reasoning suddenly appears. So in this video, we are going to understand why this works, when it works, and how reasoning emerges in AI. Let's deep dive. So, in recent years, NLP has advanced rapidly due to large language models like GPT, PaLM, where increasing model size, that's more parameters, improves performance because of the model can learn rich patterns from data. However, simply scaling model size is not enough. For tasks that requires multi-step reasoning such as math world problems, common sense reasoning or symbolic manipulation, because these tasks require understanding intermediate logical steps rather than directly predicting answers. So previous approaches tried to solve this either by training models to generate rational step-by-step explanation, which is expensive due to the need of annotated reasoning data, or by using few-shot prompting where the model learns from the few examples in the prompt. Both struggle with complex reasoning tasks. This paper combines both ideas by introducing the chain of thought prompting, where each example in the prompt includes an input, a reasoning process, and a final answer. This allows the large language models to learn reasoning patterns directly from the prompts, leading to significantly better performances on complex reasoning benchmarks like GSM-8 gave without requiring additional training image. Now, this figure 2 compares how well different AI approaches solve math problems, including GSM-8K dataset. The vertical axis shows solve rate, that's accuracy, and the bars represent 4 methods. Fine-tuned GPT-3, that's 33%, a version of GPT specifically trained on math problem. Then it is prior best, 55%, the best researcher has achieved before this paper. PaLM 542B, that's standard prompting, 18%, a very large model of 540 billion parameters, but asks question normally without reasoning step, so it performs poorly. Then PaLM for 540B, chain of thought prompting, that requires 57%. The same model but now given example that includes step-by-step reasoning, and it jumps to highest accuracy. For example, if in a problem like a cafeteria had 23 apples, used 20 and bought 6 more, standard prompting might just guess the answer, but chain of thought prompting makes the model reason. 23 minus 20 is equals to 3, then 3 plus 6 equals to 9, leading to the correct results. This figure shows that adding reasoning step can make even a general model outperform specialized fine-tuned systems, proving that how we prompt a model can be important as how we train it. Now, Chain of thought prompting is a method that enables large language model to perform multi-step reasoning by explicitly generating intermediate natural language steps before the final answer. Instead of mapping input directly to output like a standard neural network prediction, the model is prompted with example that includes reasoning steps, allowing to learn how to decompose complex tasks into smaller subproblems. For example, in a math problem, like Jane has 12 flowers, gave 2 to her mom and 3 to her dad. So that's a standard model, right? Guess the answer. But with chain of thought prompting, it learns to reason, like 12 minus 2 minus 10, then 10 minus 3, it's equals to 10. So this approach improves performance because it increases effective computation, depth, and enhances interpretability by exposing the reasoning path, and generalizes to tasks like arithmetic, common sense, and symbolic manipulations. Importantly, this reasoning ability does not require retraining. It can be elicited in sufficiently large models simply by including reasoning demonstrations in few short prompts. Now, in arithmetic reasoning, in this section, the author evaluates whether the chain of thought prompting improves the arithmetic reasoning ability of large language model using math word problems, or arithmetic reasoning is challenging for large language models because it requires multi-step symbolic manipulation and logical state. So, not just pattern recognitions, the author compared standard few short prompting where the model directly predicts answer from example, with chain of thought prompting where each example includes intermediate reasoning step. For instance, if the problem is like there are 15 apples, 15 apples ka ho gaya. If there are 15 trees and after planting more there are 21, and how many were planted? Standard prompting may guess the answer, but chain of thought allows the model to reason if 21 minus 15 is 16. They test this approach across 5 datasets, that's GSM-8K, SVAMP, ASTIV, AQUA, MAWPS, and multi-models. GPT-3, Lambda, Palm, UL2, Codex. Result shows that large language models, especially Palm 540B, achieve performance comparable to or better than fine-tuned models. We are using chain of thought promptings demonstrating that reasoning ability can be elicited through prompting alone rather than additional training. So chain of thought prompting turns language models from answer guessers into step-by-step problem solvers. Now this image is an example of chain of thought prompting across different types of reasoning tasks, that's math, common sense, symbolic, and even robot planning. Each box follows the same structure: input, reasoning, steps, final answer. For example, in the math problem, Roger has 5 tennis balls. The model doesn't just answer 11, it reasons 2 cans into 3 balls is equals to 6, then 5 plus 6 is equals to 11. In common sense reasoning, would a peak sink in water? Would a pear sink in water? The model explains the density before concluding it floats. In symbolic reasoning, like last letter concatenations, it extracts letters step by step. Y from lady, A from Gaga, or YA. Then in robot tasks, the model explains the goal. Bring something, not a fruit. Before explaining actions, these figures demonstrate that when models are given reasoning examples, they can solve different kinds of problems more accurately by thinking step by step rather than jumping directly to answers. So now this section shows that effectiveness of chain of thought prompting depends strongly on the model scale and task complexity. The key finding is that reasoning ability is the emergent properties. Small language models, or like millions of few billion parameters models, do not benefit from chain of thought because they generate fluent but logically incorrect reasoning steps, whereas very large models that 100 billion parameters or like GPT-3 175 billion or Palm 540 billion shows significant performance improvement. For example, let's take on GSM-8K, a complex maths word problem dataset, accuracy more than doubles when chain of thought prompting is used because the model learns to break problems into intermediate computations. Then, however, for simpler tasks like single operation, that's one-step arithmetic, the improvement is minimal because reasoning is not required. The results also show that large language models with chain of thought prompting can match or exceed the fine-tuned models, which normally requires additional training data or error analysis. Further reveals that larger models can make fewer semantic reasoning errors and missing step errors, showing that scaling improves both logically consistency and understanding. Think of small models like a student who memorizes formulas but don't understand why they work. So as large language models with chain of thought prompting is like a student who shows every step while solving a problem. So even if the problem changes, they can still reason it out. So now this figure shows how model size affects reasoning ability across three datasets, the GSM-8K, SVAMP, MAWPS for three models, that's Lambda, GPT and PALM. The x-axis is the model size in billions and the y-axis is the accuracy. The key pattern is that standard prompting, that's the black line, stays low as model grows, but chain of thought prompting, that's the blue line, suddenly improves performance when models becomes very large, around 100 billion. For example, on GSM-8K, a small GPT model performs poorly, but GPT-3 175 billion with chain of thought jumps to higher accuracy because it can reason step by step. Similarly, PALM 540 billion shows major gains, even surpassing prior best results. That's the orange dashed line. This demonstrates that reasoning is an emergent ability of scale, meaning large models only start reasoning properly when they are big enough and guided with step-by-step prompts. Now, in this section, the author tests why chain of thought prompting works by comparing it with three alternative prompting strategies. First, they try equation-only prompting, where the model outputs just the mathematical equations instead of full reasonings. This works only for simple problems but fails for complex ones like GSM-8K because translating language to equations requires semantic understanding. Second, they test variable compute only, where the model generates extra tokens, that's dots, to simulate more computation time. This shows no improvement, meaning reasoning gains are not due to longer outputs. Third, they test chain of thoughts after answer, where reasoning is written after the final answer. This also fails, showing that the model must reason before answering. Overall, the study proves that the improvement comes specifically from natural language intermediate reasoning, not just equations, more tokens or extra knowledge access. Like take an example, we have taken a cafeteria had 23 apples, used 20 and bought 6 more. So the equation only will give 23 plus 20 plus 6, that's 9. Work for simple problems. Now variable compute with, it will give 0, that's dot dot dot, no real reasoning. Chain of thought after answer, this gives answer equals to 9 because this is this. Too late. Now full chain of thoughts will be 23 minus 20 equals to 3, then 3 plus 6, that's 9. That's the best performance. Now, this image figure 5 compares different prompting methods on math world problems for two models, that's Lambda and PALM. The bar shows that standard prompting and variables like equation, only variables compute and reasoning after answer give small improvement, while chain of thought prompting, that's in the orange bar, gives a large boost, especially for the bigger PALM model. For example, in a problem like this only we discussed, the equation prompting might be just this, we discussed all this earlier, and the chain of thought is performing the best. So the improvement specifically comes from the natural language reasoning steps, not just writing equations or generating more tokens. Now this section, it studies whether the effectiveness of chain of thought prompting depends on the specific examples or writing used in the prompt. In prompting, based learning performance can be sensitive to how examples are ordered or written. So the author tests robustness by using chains of thought written by different annotators, varying the exemplars, sets, and changing the order. For example, one annotator might explain a math problem in multiple short steps, while other writes a concise explanation. Despite these stylish differences, the model still performs significantly better than standard prompting. This shows that improvement comes from the reasoning structure, not from the exact word. They also test different exemplar selections and numbers, and the results remain consistent, demonstrating that chain of thought prompting is robust to prompt variation and generalizes across tasks, datasets, and models. Now this image, that figure 6, shows the chain of thought prompting is robust, meaning it works well even when the reasoning examples change. The bars compare standard prompting, that's in the yellow, with different version of chain of thought prompts written by different annotators in different styles or using different example sets. On both datasets, that GSM-8K and MAWPS, standard prompting has a lowest accuracy, while the chain of thought version performs much better, even though their styles are different. For example, one annotator might explain a problem in a many small steps, while another uses a concise explanations, but both still improve performance. This shows that the benefit comes from the presence of reasoning steps, not from the exact wording or the specific examples, proving that chain of thought prompting is stable and generalizable. Now this section shows chain of thought prompting is not limited to arithmetic tasks but also improves performance on common sense reasoning, which requires understanding real world knowledge and multi-step logical inference. Common sense related reasoning task involves interpreting physical situations, human behavior, or contextual information, such as determining whether a statement is plausible, that the example that would a beer sink in water, or inferring a sequence of events like what date was 10 days ago. The authors evaluate this on 5 benchmarks. First, CSQA, StrategyQA, date understanding, sports understanding, and SayCan. That's robot planning. Using few short prompts with reasoning steps, large models show significant performance gains compared to standard prompting, sometimes even outperforming human baselines. For examples, in a sports reasoning task, the model reasons that João Moutinho is a soccer player, so he wouldn't catch a pass in American football game. Demonstrating semantic understanding, this shows, for example, on GSM shows that natural language reasoning allows models to generalize beyond numerical problems to broader cognitive tasks. Think of a common sense reasoning like understanding everyday situations. If I say it's raining and I forgot my umbrella, you know I will get wet. Chain of thought prompting helps AI make these kinds of logical connections. So this figure 7 shows how chain of thought prompting improves common sense reasoning across 5 tasks: CSQA, StrategyQA, date, sports, SayCan. As model size increases, the x-axis is model scale in billion parameters and y-scale is the accuracy. The blue line is the chain of thoughts consistently performs better than the black line, that's the standard prompting. Especially for larger models like PALM 540B. For example, in a sport task, the model reasons like the João is a soccer player, so he wouldn't catch a pass in American football, leading to higher accuracy. In SayCan, that's the robot planning, the model explains its steps before choosing actions like deciding to bring an energy bar because it's not a fruit. The green dash shows human performance, and in some tasks, the model approaches or even exceeds it. These figures demonstrate that reasoning steps help model understand real-world situations, not just math. Now, in this section, the authors evaluate chain of thought prompting in symbolic reasoning, which requires models to manipulate symbols using logical rules rather than relying on semantic knowledge. These tasks, such as letter concatenations like Army Brown YN, and then coin flip state tracking, test whether models can follow structured procedures, standard prompting often fails because the model treats the task as a pattern matching, but chain of thought prompting enables step-by-step reasoning. Example, identifying each last letter from concatenation in of counting flips to determine parity. The experiment shows that large language models like PALM achieve near perfect performance, especially when solving long sequences not seen during training. So this demonstrates length generalizes, meaning the model can apply the same reasoning process to more complex inputs, similar to how a human applies the same rule repeatedly. For example, if I trained are two-word names, the model can still correctly concatenate letters from four-word names when reasoning steps are provided. Say, think of symbolic reasoning like I follow a rule. If I tell you to take the last letter of each word, you can do it for any number of words. So chain of thought prompting helps AI follow the rules step by step, even for longer inputs. Now, this figure 8 shows how chain of thought prompting helps language models solve symbolic reasoning tasks, especially as a model size increases. The top graphs are for the last letter concatenation, and the bottom graphs are for the coin flip task. These are tracking whether a coin is heads after multiple flips. The left side of each pair is in domain, and the right side is out of domain, meaning harder classes with longer sequences than seen before. The blue line is a chain of thought, rises sharply for large language models, showing near perfect accuracy, while black line is the standard prompting, stays low, especially in harder cases. For example, if the model learns to concatenate last letters of two-word names, chain of thought lets it apply the same reasoning to four-word names. Similarity in coin flips, it learns to coin flip step by step, even versus odd, to determine the final state. This shows that reasoning steps helps models generalize rules to more complex situations. Now the discussion summarizes the chain of thought prompting in is a simple yet powerful technique to elicit multiple step reasoning in large language models without adding any additional training. The experiment across arithmetic, common sense, symbolic tasks show reasoning ability emerges as a function of model scale, meaning Larger models can leverage step-by-step natural language reasoning to solve tasks that standard prompting cannot. For example, instead of directly answering a math question, a model can reason through intermediate steps, then improving both accuracy and interpretability. The author also highlights limitations. That's how reasoning chains may still contain logical errors. Reasoning ability only appears in very large models, making deployment costly. Another, it remains unclear whether models truly reasons or simply mimic reasoning patterns. Overall, the work suggests that prompting strategies can expand the set of tasks solvable, but LLMs and opens new research directions for improving reasoning in smaller models. Once they learn to reason step by step, they can solve harder problems. But if the student is too young, like a small model, this method doesn't work yet. Chain of thought prompting reveals hidden reasoning abilities in a large language models, but true reasoning and efficiency remain open challenges. Thank you for this video. Hope you have learned all things about chain of thought. I have tried my best to explain you all, guys. Thank you. Is that natural